So the superposition principle is the idea that when waves overlap, they'll interfere with each other, and they can result in destructive or constructive interference. But what you're basically doing is adding the amplitude of each wave together, or the displacement of each wave at each point together, to give you the overall wave. So in this case, we've got one wave travelling that way and then the other wave travelling the other way. When they meet together in the middle, because they're both in phase, they both have they're both peaks, they add together to produce a peak that's twice the height, and then this wave continues going in that direction and this wave continues going in that direction. So although they interact, they don't affect the actual travel of the wave, each individual wave. So that's what constructive interference looks like. And a few of the videos we've watched have alluded to constructive interference. The one on Young's double slit experiment we watched yesterday certainly did. In this case, we've got two waves that are 180 degrees out of phase. So when they meet in the middle, they cancel each other out. So we end up with a flat line. But the two waves are still there. Remember that waves is the transfer of energy without the movement of without the transfer of particles. So even though it appears that the particles have undergone no displacement at this point in time, the two waves are still there. So the next instant of time, the wave continues in that direction and the wave continues in that direction. So the two waves haven't disappeared, they've just overlapped to negate each other's displacement. Okay? So we can look at that in, the first example is just 1D, this is in 2D. So coherent waves have a phase relationship, whereas incoherent means that the phase relationships are just random and you can't really identify good patterns out of them. So we can get interference patterns when we've got a consistent or coherent waves. So you can see in this case here that we've got two sources, each emitting, producing semicircular waves. The thick line is the peak and the thin line is the trough. So where you get two peaks overlapping, you get constructive interference. Where you get a peak and a trough overlapping, like here, you get destructive interference. And we saw that idea on the video yesterday with the water, where he was bobbing the two balls in the water, producing those waves going out, and they highlighted the areas where you could see the waves constructively interfering and destructively interfering. And we'll do this in a moment with sound waves using the two speakers. We'll go and find in the classroom spots where the sound is constructively and destructively interfering. So the lines joining the points are the antinodes or antinodal lines. So if we look at Young's double slit experiment, which is the first experiment that was that disproved Newton's idea of the corpuscle, and it meant that as a result, Huygens' idea on light acting as a wave was more widely accepted, and Newton's idea was rejected, because if we're shining monochromatic light, so light with a single wavelength, single frequently, through a double slit, if what light was made up of particles, then you would expect to see two lines, which, if you remember the guy in the yellow shirt yesterday, that's what he thought he was going to see, was just two lines.
Wouldn't it be like, it's not that really dumb. Like, wouldn't some particles hit the edge but not fully and slow down and pull upwards a little bit and pull down?
Some particles kind of bounce, but if that edge was perfectly flat, then the particles, if they hit the edge, then they'll bounce back. Yep. So that's what you would expect if light behaved as a particle. But this is what was observed. So as we know, you get a series of bands. The monochromatic light is a coherent light. It's gone through the double slit. You get diffraction on either side of the double slit. And as a result, as they spread outwards, they constructively and destructively interfere with each other. These are the lines of constructive interference, and these dark patches in between are the lines of destructive interference. So we need to be able to explain how this works.
So
Yep.
in the video, it was dark, even though like it was 2 slits.
The slits would have been quite short,
Okay.
I think. Yep. So it's superposition that's occurring that produces the light and dark patches. So where we get constructive interference, we get a light patch. Where we get destructive interference, we get a dark patch. And the whole idea is that when when you get a light ray coming from here and a light ray coming from here, if their wavelengths or the path that they travel is half a wavelength different, or a multiple of half a wavelength, so half, 1.5, 2.5, 3.5 wavelengths, then they will be 180 degrees out of phase and they'll destructively interfere. Whereas if they're a whole wavelength out of phase, they will constructively... Sorry, if they're in phase, but the path difference is a whole wavelength or a multiple of a whole wavelength, then they will be in phase and constructively interfere.
Will we be needing to do like calculations how like last year, so like 2 speak and...
Well, we're not dealing with waves in particular. We're dealing with, from this point of view, we're using it to describe evidence for light being a wave. Yeah. So the reason why we shine light through a single slit before we go through the double slit is just to make sure that our light is coherent as it goes through. Okay?
So it's coming from one source.
Yep.
Not like bouncing.
Yep. So using the relationships, he was able to find, Young was able to work out the wavelength of the light pretty accurately. And considering that the wavelength is in the hundreds of nanometers, is in nanometers, which is 10 to the minus 9, then it's a pretty good effort to do that. So it's basically using the path difference is d sine theta, where d is the distance between the slits and theta is the angle counted, the angle away from the shown better on this slide. So yeah, so d sine theta is a multiple of the wavelength. So where d sine theta is an even multiple, then you'll get constructive interference. So that's the extra path distance that the light wave has travelled, and if that extra path difference is a whole wavelength, then you get constructive interference in that case. So that's the setup of Young's double slit experiment, which we need to be able to explain, we need to be able to draw. So when we're drawing these wave fronts, what are some of the things that we need to consider when we're drawing them?
Equal space.
Equally spaced. What do you mean by equally spaced?
The wavelength is the same.
The wavelength is the same. So the distance between the crests, which is what these lines are representing, will be the same, and it will be the same throughout the experiment because, as we learnt yesterday, the wavelength, frequency and velocity doesn't change because the medium's not changing. Okay? All right, so that's superposition. What I'll do